Hello, in this video I'm going to go over how to solve a statically indeterminate torsion problem. This problem deals with somewhat of a special case where even though the shaft is clamped on both ends, one of the clamps allows a degree of movement before it'll catch and apply its own reaction. So as you can see, it's a cylindrical shaft. This is viewed from the side that is made of steel, 1.1 meters long, and a diameter of 20 millimeters. The right clamp allows an amount of slip of 0.6 radians before it catches. And 300 millimeters from the left, there is a 20,000 Newton meter torque applied in the clockwise direction when viewed from the right. So we're going to go through the standard 4-step process, 3 or 4-step process, and how you factor in this amount of slip or misalignment really comes down into the equation where you calculate the reactionary torque in the right clamp. So let's go ahead and get started and solve through this problem. So we can bring up torsion. Okay. So break it down into segments. It's one uniform segment. .1 meters, 20 millimeters diameter, gigapascals. Moment of inertia, I've calculated here. Okay, 1 torque applied, 0.3 meters from the left. It's negative because it's clockwise. It's 20,000 Newton meters. Okay, so now we have an amount of misalignment, which is 0.6 radians. Okay, so you can see the 3 main steps still the same as before. First time through, remove the right clamp, solve for twist, the net twist. Second time through, remove the right clamp, end all torques, and then apply a positive unit torque on the right end, which would be counterclockwise, and solve for the net twist. And then with those 2 net twists, you can calculate what the reactionary torque in the right clamp is. Okay. So the calculation should be fairly easy because it's just a solid shaft. Of course, when you remove the right clamp, there is no longer any torque applied on section 2. So that's just zero amount of twist. Moving on to section 1, you can see sum up your moments. I have stress and strain calculated even though we're just looking for twist, so you can just go straight for the twist once you have your reactionary torque. And that's negative 4.494 radians, which is itself the net amount of twist in step 1. And as it's negative, that means it's twisting in the clockwise direction. As you would expect, the torque is in the clockwise direction. Okay, step 2, we've removed the right clamp and applied a positive 1 unit load. Again, stress and strain are calculated, but we only care about the twist. And the program, it asks for just the net twist right up front of the entire segment. So we're going to have to sum the 2 segments amount of twist up. Here's section 1, still that just 1 Newton meter. And it ends up having less than half of the amount of twist as section 2, and understandable because it has less than half the amount of length as section 2. But we can sum those two up and we have our net twist. Okay. So there we go. Once you put those in, then it solves for the torque at the right clamp. But that is the crucial point of this video, and we're going to go into the actual equation that you use for that. Okay, so whereas before, when there was no amount of slip, you could simply just take the negative of the net twist of step 1 divided by the net twist of step 2. However, now we have the slip involved, and the equation is somewhat different. And remember, one of the crucial things for this equation is that the amount of twist overall is going to be greater than the amount of slip. That is, once you apply the torque, if the torque was not enough to twist the shaft at least the amount of allowed misalignment, then the right clamp would never engage, and it's just a standard determinate problem. There would be no reactionary torque. So as long as the torque is more than enough to twist it that allowed amount, then you're going to have that reactionary torque, and you're going to have to use this equation. So it's the net twist of step 1 divided by the magnitude of the net twist of step 1, then multiply that by this magnitude minus the amount of slip, divide by net twist of 2, which comes out to 4,726 Newton meters, and this still follows standard sign convention. And you can see this is also the same value that our program has given us. So once we have that, then you can apply that in the right end and solve as a standard determinate problem. And this time, the amount of shear stress is actually needed to put it in the program. So this outer torque is going to be that 4,726. Remember, for shear stress, you want the magnitude values. Okay, and the amount of twist. Finally, section 1. Adding into that summation of moments, we have that counterclockwise amount. And as you can see, this comes down to a reactionary load that is negative, so the actual reaction of the left clamp is going to be counterclockwise. As you would expect, both clamps are trying to turn it counterclockwise as the load is trying to turn it clockwise. Don't forget magnitude of shear stress. So even though it's negative, I'm going to put in positive its magnitude. And finally, the amount of twist. Okay, and do notice that when you sum up these two amounts of twist, the final net twist is negative 0.6 radians, which is the allowed amount of slip before that right clamp was going to catch. And it's negative, which means it's clockwise. It's in the direction that it should be with the torque. So intuitively, it makes sense. And that's basically it. That's how you approach it when you have an allowed amount of slip. It's just that equation, this equation, is going to be different. And remember, as long as the amount of torque is going to make it twist more than the misalignment amount, then you're going to have an indeterminate problem. If it's not going to twist it enough, then you just have a normal determinate problem, because you're never going to have that reaction from the right clamp.